Hey everyone, Will Cook here, bringing you an update to the progress in the next release of GymFC version 0.2. In this next release, I'm super excited about. It's going to allow for the support of any aircraft, and also it's going to have a more generic front-facing agent interface so that you can not only use it still for intelligent flight control system training, but also doing any sort of flight control, whether that's just generic PID, backstepping, or really anything that you want to test out. So should be very exciting. It's taken quite a bit longer than expected because it is a complete rewrite and the architecture is way more complex, but I'll be releasing some videos specifically to the new version in the next couple weeks or so. Now, during our development of our higher fidelity quadcopter model that more accurately reflects the aircraft that we're transferring our trained neural network to and compiling it into NeuroFlight, we observed some simulation instabilities that would occur at high angular velocity. And this primarily is due to the additional links that are required when you're generating higher fidelity aircraft models. And I wanted to go over what we found just so that anybody that is doing research with GymFC or just Gazebo in general, you'll know what to look for and how you can actually solve these issues. Now, in the original GymFC, it wasn't very flexible. We included the Iris quadcopter model, and this was primarily just for simplicity, and it was easy to get starting because this model is actually included with Gazebo, so we already had it. However, the model itself only has about 5 links, which include the main body, and the main body encapsulates the battery, each of the motors, and it also assumes that there's a uniform density, which is just completely inaccurate. We all know those that are building quadcopters, especially those used for racing or even freestyle, the battery is going to have, in many times, the majority of the weight, and we're going to have a very uneven distribution from where the actual battery is, somewhere hopefully along center of thrust, to where our additional weight of the motors are at the end of each of the arms. Now, when we're making higher fidelity models, our only option at the moment with Gazebo and working with SDF is to create individual links for each of the component, and it's quite tedious, but what this allows us to do is to then create all the geometric measurements for each one of the links, such as our inertia, our mass, and get a more realistic representation of what the actual model looks like. So we went from using the default Iris quadcopter model. For our specific research, our new aircraft digital twin model that we've created now has a total of 11 links to include all the propellers, the motors, the flight control stack, the frame, and the battery. Now, with the addition of these links, we were able to observe some interesting instabilities in the simulator that you should be aware of when you're creating your own aircraft models. So let's take a look at that. Okay, I'm going to be running one of the test scripts that's going to be included in the next release, and these collection of test scripts are really there to help you make sure that the communication between that GymFC can communicate back and forth with your aircraft model. And the test that I'm going to run is going to allow us to specify certain control signals so that we can make sure that everything looks like it's operating correctly. Now, I can choose to do a variety of different commands, but what I specifically want for this demo is just to show you yaw, so we can do it. Okay. So here every single time I press the enter key, it's going to provide one iteration or one step in the simulator. Now I'm going to provide many steps, and we're going to see the behavior with these links. Now I should point out that I modified the maximum velocities of these motors in this example just to give you more of an exaggerated viewpoint of how bad the instabilities can actually occur. But for instance, this is not something realistically you'd see. For the spit out of the console right here, this is basically saying that we're currently yawing at 15,000 degrees per second, which is a little ridiculous, but I just want to get this demo and show you the exaggerated effects that it can have. Now, what we can see here is when we have these extremely high, most likely unrealistic angular velocities for this specific example, we could see that all of the propellers have completely drifted and separated from the model, and also all the motors. What we would like to do now is understand how big of an issue this actually is, how much a drift is actually occurring. Now, as I previously mentioned in the beginning, our aircraft model has a total of 11 links currently. If you're into FPV racing, you'll notice that I currently don't have a model yet for the antenna VTX and the camera, which we'll probably add in later. But right now we have a total of 11. We're treating the flight control stack for simplicity just as one single block, one single link. So I just created a pretty simple algorithm in which we treat the distance or the connection between each link in this as an undirected graph, in which each edge is going to be the distance in meters between each link, and then the vertex is going to be the center of mass of each of the link. And this illustration right here is for a single, starting at a single vertex or vertice for this propeller, and we have the connection to all other k-1, or sorry, if v is the total number of vertices, v-1 other links that we have. Now, when we create this entire graph, we do this for each specific link that we have. So we have an entire graph representing from each link what the distance is to all other links. Now, the graph here is defined by the actual simulation time, and when the simulation just starts, so at t equals 0, we take essentially a snapshot of what the state is at rest, and we use this as essentially our baseline. We assume that since no angular velocity, that the aircraft isn't achieving any sort of angular velocity, it's at rest, that all of the links should be at their resting position. Then at each time step of the simulation, we recompute the graph, or really just measuring the edges between all the links. We sum those values up, and then we take the difference and then the absolute to get essentially what a sum of the delta distances between all the links. And this value here, delta ET, at each simulation step will give us a basic understanding of how bad the actual drifting is occurring between these links. We want this to be 0, so any non-zero value here is a real problem. Alright, so what I ended up doing is starting off with all the permutations of the motor control signals we can give our aircraft, and we perform an experiment in which we're measuring the delta ET for each one of these, I guess you could say, trajectories. So the goal here is to excite all the different combinations and all the different angular velocities that the aircraft can actually achieve by going through the permutations of the different control signals. For example, the first permutation would just be that we want 100% throttle on motor 1 while the other 3 motors are just at 0, and then that would be one of these like trajectories for some specific angular velocity that it ends up achieving. When we actually like observe this behavior, some of these are completely unrealistic for the data that we actually tested it on, but this is just giving a basic understanding of how intense that this drifting between the links can actually be. Now, if we look at the color bar to the right here, this would be what the delta ET would be, and this is the model drift in meters. So when you see something that is yellow, that's 0.35 meters or 350 millimeters that in total the links all drifted apart. That's crazy. That basically means the model exploded. And as I previously mentioned, we want to see this drift being 0. So just given that there's a color change, we have an issue here. Alright, so what is going on here? Why is there drifting? Well, if you're familiar with rigid body dynamics and simulating this is going to be nothing new to you, but I'm not an expert in this area, so this was definitely a surprise to me. And if you're just using Gazebo by default, then this might be something new to you as well. Well, by default, when you just install Gazebo, it uses the Open Dynamics engine as the default physics engine. And ODE is a maximal coordinate solver, which means that essentially it's modeling and treating each individual link. So we have our propeller, our motor, and our frame as separate rigid bodies. And during a single simulation time step, each of the forces, torques, and everything is being computed for each rigid body. And then at the end of the simulation, the constraints that were specified between all these links is then enforced, and you have to specify these actual constraints. So because they're all being modeled separately and then combined together based on what other constraints are defined, if you look at the literature or you've taken any classes or done anything in this space, then it's pretty well known that maximum coordinate solvers cause bodies to drift due to coordinate redundancies. Now, there's actually a fair amount of information on this stuff, like out there, if you want, if you're looking for like details on it. Okay, so what other options we have? Clearly, this is completely unacceptable for our specific task of doing flight control systems, in which we're dealing with extreme angular velocities and high performance type aircraft. We need to make sure that there's zero drifting that actually occurs. Well, luckily, there is something known as generalized coordinates, and when you use generalized coordinates, this is also referred to as reduced coordinates, in which we're only specifying or defining the actual like model by the number of degrees of freedom of the system. So things become reduced, and only the simulator is only going to be simulating the specific degrees of freedom of that system. So we have our SDF file is specifying that the link between the motor and the frame is fixed, and really the only degree of freedom we have is the propeller rotating along the z-axis of the shaft of the motor. Now, there are two options in Gazebo that we can use for that support generalized coordinates, and that's DART, the Dynamic Animation and Robotics Toolkit, and SimBody. We recommend using DART moving forward for GymFC because Dart specifically is created for the task of doing things such as like robotic control. Okay, now that's all great, but how do we use Dart? Well, unfortunately, it's not as straightforward as the default of ODE that comes with Gazebo. You actually, in order to use Dart, need to install Gazebo from source, and it will then build in the support for Dart, and then you have to include all the additional extra libraries if depending on how you want your build to go. We followed the instructions pretty much verbatim on the Gazebo website, building from source on Ubuntu, the latest LTS, and it was very straightforward. We put it on 5 machines and only had one hiccup because the Dart repositories were changing so drastically. But if you install Dart from source as well using version 6.7, haven't had an issue yet, and it's pretty smooth to install. Okay, now once we have Dart installed, how do we go about enabling it? Well, there are multiple ways to do this in Gazebo. I think you can do it at the command line, but for GymFC, we do this through the world file, and I'm going to disable or comment out using ODE, and we specify in the attribute type for the physics tag in our world what physics engine we're going to use. And there are 4 that are possible: ODE, Dart, SimBody, and then also Bullet. So now let's rerun our experiment and let's see if any drifting occurs. Okay, now let's go back and we're just going to test out yaw again. Here we can see the quadcopter and a very aggressive, unrealistic angular velocity of around 25,000 degrees per second. But again, this is to demonstrate the stability of the simulator. And as we can see even from this distance, there is absolutely no drift occurring. Zoom in a little bit closer. Everything is attached as expected and as desired. No issues. Let's get out of here. The same experiment was run again, where we're exciting all the different motor permutations, except this time we're doing it using the Dart physics engine. And as we can see here, there is absolutely no drift that's actually occurring between these links. Here, if we're looking at the color bar, these values are 1e to the negative 13. So we have essentially the behavior that we are expecting and that we desire. Now, in conclusion, to create more accurate and higher fidelity aircraft models, we must use additional links. I have combed through some of the Gazebo pull requests and discussions in which there has been discussion on how we can actually go about creating different inertia and geometric parameters for single links. However, it's just not there yet, and this is really the only way we can get around this is by creating multiple links. But when we increase links, we're now prone to model instabilities when using maximal coordinate solvers such as the default ODE. Now, we can create stable simulations by using a generalized coordinate solver such as Dart, Or what we also found to be effective is you can decrease the step size. The problem with decreasing the step size, we're currently by default stepping at 0.001 seconds, which is 1,000 hertz, equivalent to 1,000 hertz. Any more decreasing the step size is going to increase the actual time it takes to do any sort of training. And when we're doing training for days at a time, I really don't want to go down that route of having to increase the training even further. So I think the best option moving forward is by using Dart, and the actual stability scripts will be included in the next release, so you'll be able to play around, and if your actual aircraft does not perform very aggressive maneuvers, using ODE still might be okay for you. But to be on the safe side and to make sure that you're removing any sort of additional errors into your training and your simulation, using a coordinate solver will just make sure that it's just one less thing that could be causing issues. So if you have any questions, please leave a comment. And if this was unknown to you, I hope that you took something away from this video. And I'll be posting hopefully more videos now that I'm just about done teaching for the semester and can make some more progress on GymFC. All right, until next time.